because what was your name? Kate came this morning at 10, and I'm not sure. I checked with my undergraduate course because I have office hours. I knew that this could possibly be 4 times, Mondays and Fridays, and 10 and 4, and I might have gotten it mixed up, but my undergraduate class confirmed that it was the 4 p.m. that's both Monday and Friday, and the 10 was only Friday. Okay, I guess I got. You were Kate, right? Let me try some more names. You're? Divya. Divya? Okay, so let me write. I'm writing them down. So Divya, not that I'll remember any, but are you a graduate student? What year? I'm a second-year grad student. And who's your advisor? Okay, and Kate, your first year, and maybe Hammond. Let's see. You don't look like one of the faces that I did last time, or have I already forgotten you? Jason, okay. You're not written down over here. And what year? First year. And tell me your name. Jennifer. Now it's time. Can we start? Okay. So let me stare at your faces a little more, but it won't do me much good. Okay. So if I said it wrong last time, this is what I meant to say. So I have some handouts because the basic thing about tracing rays against spheres and planes and polygons was not in our textbook, and Kate told me that the code that I made available to you talked about intersecting with planes but not intersecting with triangles or polygons. So this is photocopied out of another ray tracing book by Peter Shirley, and I'm going to go over the ray-sphere intersection. In fact, the actual mathematics in there will generalize to a ray ellipsoid equation. It's just the quadratic equation is a little bit different. But in general, if we have a ray equation parameterized, I should have probably put it in the other order. Parameterized ray equation. The ray as a function of the distance parameter is the origin plus the distance times the unit direction vector. And then we have an implicit surface equation. Say f of x, y, z, or f of some point equals 0, which I'll write in a minute for the case of a sphere, but you can have an implicit equation for an ellipsoid or something that's the union of a bunch of Gaussian potentials that people use for blobby modeling of molecules and creatures and so on. Any function, then the surface defined by that function, if you substitute the ray, here's the origin, and here is this ray starting from the origin in direction d, and find out the value of t that makes f of p be 0. In other words, f of r of t equals 0. That will turn out to be a single equation in the parameter t. And in this case of this kind of shape, we have 2 intersections for this ray, and maybe for this ray we've got 4. And if you only want the first intersection, you just have to put them in order and find the least t. So that's what we want to do for a sphere. So the equation for a sphere, I might just, if I could find my notes, I'll read from those instead of from the photocopy, but it's basically the same thing. If we have a sphere, the sphere has a center C, and radius r, and the equation of the sphere says that for any point on the sphere, the difference between that point and the center position squared equals r squared. Really, I could just say the distance, p minus c, equals r, right? This point here has less than r distance. This point here has more, and one that's right on the sphere, it'll be equal. But then there's a square root involved. So it's easier to write it this way, because then we can actually represent the absolute value of a vector by dotting the vector with itself. So before I do that, though, let me put my origin and my direction vector, and here is this ray. I guess this ray will intersect the sphere twice. Here's the direction vector, and for this point P, I'll put the ray equation O plus TD, and then minus C, I may forget these vector signs, squared equals r squared. So let's see, let me take the terms with t separately. So I'm going to say TD and then plus a constant vector O minus C squared equals r squared. And then maybe I'll go to the next board. This thing can be expressed as a dot product. The length squared of any vector is the dot product of that vector with itself. So if I write it like that, then I can end up getting the quadratic equation I was talking about in T. So I'm going to say TD plus the vector O minus C dotted with TD plus the vector O minus C equals r squared. And then I'm going to multiply this out. This is like a plus b squared. You know, this is quantity a and b, and it's like a plus b dotted with a plus b. And you can say it's a dot a plus 2a dot b plus b dot b, right? That's just multiplying out by the distributive law. So that's what I want to do here. I want to multiply these out so that this is my a and this is my b. I'm going to get t squared d dot d when I take this dot that, and then I have this dot that and this dot that, but doesn't make any order what you do the dot product in, so I'm going to get twice t times d dot the origin minus c plus the origin minus c dot itself. And then I'm going to say minus r squared equals 0. I'm going to bring the r squared to the other side just because I want it to the form f of something equals 0. And so I can say this is a t squared. This d dot d is a scalar, so this much is my a, plus, do I want to keep the 2 in there? Maybe not. B times d dot o minus c. Plus, oh, I didn't want to do that, did I? I just wanted to keep it d just times t. This b, so a is d dot d, b is 2 times d dot o minus c, where I'm leaving off my vector signs. And my constant term on the quadratic equation is going to be o minus c dot o minus c minus r squared. And then it's going to look like the form at squared plus bt plus c equals 0, which is, as I promised, the quadratic equation in this unknown value t. So who remembers the quadratic formula for the roots of a quadratic equation? If I have a quadratic equation of this form, when I was in high school, I memorized the formula for the roots. And when I was in high school, they derived that formula by the technique of completing the squares. But I'm not going to rederive it for you. If nobody remembers the formula, I'm just going to copy it. Anybody remember it?
Square root of the discriminant.
Which is what?
B squared minus 4ac.
Okay, and it happens that b is a multiple of 2 here. So we're going to end up factoring that out. Let's see if I've already done that in this step. I guess not. I haven't done the whole algebra. But it turns out that b has a factor of 2, b squared has a factor 2, and this has a factor of 2 in it, 4. I mean, and you take out the square, there's a 2. So if you actually write this, you could write a different formula when b is a multiple of 2, and save you 1 multiplied by 2 maybe. But basically, you have these 3 quantities in the standard quadratic equation, and in general, you're going to get 2 roots. But you might get 0 roots or 1 root. What are the occasions when you get 0 root? What would that mean geometrically? No intersection, like this. And what about when you get 1 root? Just tangent. Okay, well, I did this for a very simple sphere, but you could do that for an ellipse, which also has a quadratic equation. And, I wrote these as dot products, but if you know the components in terms of x, y, z coordinates of these, the D and the O and the center, then you can do the arithmetic and get capital A, B, C in terms of those coordinates. Okay, so it may be, though, that your viewpoint, your initial origin is here, and the direction vector is like that. And then the 2 intersections you're going to get are actually going to be negative values of t. They're behind the origin on this ray. And they're no good. So in that case, the ray, if it starts here, we're only interested really in positive t when we're tracing along the ray for computer graphics. So those aren't any good. Also, if the ray origin is just inside here, and you're tracing like that, you're going to have 1 positive root and 1 negative root. So what you want is the smallest positive root, if any. So now, if we look over here, B could be either positive or negative, depending on whether this direction vector makes, here I guess it's 0. It's exactly perpendicular. But if this direction vector is like this, compared to that, then you're heading away from the sphere. And if the direction vector is like this compared with the direct vector O minus C, then you're heading toward the sphere. So I think what's happening, this A is always positive, right? So because it's a dot product of 2 things. It's a dot product of a vector with itself. So I guess if you want the smallest root, you always want to use the minus sign here. And then if the smallest root, it gives you a negative number, then you want to try the plus root. And if that also gives you a negative number, then you've got no intersections. Okay, so now how about sphere plane intersection? Well, if we have a plane, say it's the plane of the 3 points A, B, and C. Actually, that triangle goes clockwise, but that's okay. Since I've drawn it this way, I'll keep it. Usually you want to orient your triangles so they look counterclockwise from the outside. But I guess whoever created your database, you can't guarantee that worked anyway. So I can find a plane going through these triangles with some cross products. Namely, I can find the normal to the plane by taking, say, A minus B cross A minus C. And that will be perpendicular to the plane of this blackboard if this triangle is on this blackboard. So n equals A minus B cross A minus C. And then I can find a unit normal. It's not always needed. In fact, for this application, it isn't. But I like to think in terms of unit normal. So it's n divided by its absolute value. And now I can say, and in fact, in this particular case, since my right-hand rules, because my triangle actually was clockwise when viewed from our side of the blackboard, my right-hand rule gives me a normal that's actually pointing into the blackboard in this case. So if I have a point behind the blackboard and I take P minus A, actually I can use any point and dot it with this unit normal vector, I'm going to get a negative number. If I take a point P, which is right on the blackboard, I'm going to get 0. And if I take a P that's on my side of the blackboard, I'm going to get a negative number. Right? So P is sort of, this normal is sort of the outward normal. It's the pointing toward the direction. If you view that triangle, it's going to look like the ABC was going counterclockwise, which in this case means we have to view it from behind the blackboard. So behind the blackboard is positive, 0 is on the blackboard, and in front of the blackboard is negative. So that means this is an implicit equation also for a point P. So if we again put R of t minus any vertex of the triangle dot n equals 0, then we get a single linear equation, right? Because this everything is constant and R of t is linear in t. So it's going to be a linear equation. And if we solve that linear equation for t, we're going to get how far along the ray, here's the origin, and somewhere, actually I better draw that triangle in a different plane. Assume the triangle is here, on a plane that isn't quite on the blackboard, and you start from the origin and you move in direction D, and see how far you go before that ray hits the triangle, hits that plane. And that's your intersection point. So ray-plane intersection is another case of this implicit equation. The problem is to decide whether this point, say P, that we got by solving this equation is inside the triangle or not. And I guess that's the point where the code that I put online for you doesn't do. So I remember now when I taught this course before, other students just like to understand things like camera motion or depth of field. If you like put a checkerboard texture on the plane by using some sort of coordinate system on the plane to look up a texture, you could like make black and white or red and black patterns, and you could see those have a depth of field effect. But if you really have a model made out of triangles, we still have a point in triangle calculation. So I'm going to tell you two ways to do that. The one is to try and parameterize the plane. And what we're going to do is think of, here is the vector, here's A, here's B, and here is C. And we think of these two vectors as parameters on the plane. Right, so any point on the plane is A plus a certain, A is a given point on the plane, and then we can have a certain multiple of this direction and another multiple of this direction, and that will give us any point on that plane, right? Because these two vectors are sort of a basis vector for moving along that plane. So we can think of it as beta times B minus A plus gamma times C minus A. And the way they derived it on the sheets I handed out is to say that any point on the plane can also be thought of as a sum of alpha times A plus beta times B plus gamma times C, and these are called the barycentric coordinates of this point with respect to the vertices of the triangle. And in fact, you can get alpha by looking at the ratio of the area of this triangle to the area of the whole triangle, and beta by the ratio of the area of this triangle to the whole triangle, and gamma by the ratio of this triangle to the whole triangle. Or in terms, you could just take in terms of ratios of altitudes, ratio of this altitude to this altitude of the whole triangle. If these were perpendicular, actually they don't look perpendicular. But those have the property that alpha plus beta plus gamma equals 1. So to write this equation, another way of looking at it is just alpha equals 1 minus beta minus gamma. Right? So the 1 gives you the A, and the minus beta is the minus A here. And the minus gamma here, when you have alpha times A, gives you this one. And then you have the beta times B and the gamma times C from these two terms. But in both cases, either interpreting these two as basis vectors for the plane relative to point A, or in terms of barycentric coordinates, you still have conditions for staying inside the triangle. So in terms of barycentric coordinates, it's 0 less than or equal to alpha, 0 less than or equal to beta, and in other words, they all have to be positive. And this condition, if alpha equals 1 minus beta minus gamma, that says 1 minus beta minus gamma is, I guess I should just say greater than or equal to 0. That means, if I bring these to the other side, beta minus gamma, beta plus gamma is less than or equal to 1. So in terms of beta and gamma only, in terms of this representation, we have these three conditions. Beta and gamma are non-negative, and they add up to some number less than 1. So now we can intersect a ray with a parametrized surface instead. So basically, we have some surface, I don't know, why don't I call it Q of beta and gamma, which is a parametrized surface. And now we're not directly substituting in this equation like we did with an implicit surface. We're trying to find the parameters beta and gamma. So what we really need to solve, the ray equation of T equals this parametrized surface in terms of beta and gamma. Right? So another case would be, say you have a bicubic patch. Q, usually we use U and V for the parameters. Then, again, we'd have three unknowns, T in the ray and U and V for the parameters. Here I just called them beta and gamma to follow the sheets I handed out. So we have three unknowns. Two of those unknowns say where on the surface the point is, and the third says where on the ray, and we're trying to find values of all three to make these coincide. But really, these are three equations and three unknowns, because there's x, y, and z coordinates for each of these three things. So we have three equations for three unknowns, and you could then, say, intersect a ray with a bicubic patch. But those equations, if it was bicubic, would be higher order. Because this is linear in beta and gamma, we're just going to get three linear equations for three unknowns. Let me see if they're in great detail there, but let me write it in this equation for the case we have. O plus TD equals A plus beta B minus A plus gamma C minus A. So basically, our equations say, here are the unknowns, beta, gamma, and T. And what's multiplying them, let's see, how can we do this? I want to put something on the, let me erase this and let me write it so that my terms that multiply the t, beta, and gamma are on the left and the constant terms are on the right. So that means I have beta b minus a plus gamma c minus a plus t times the vector d equals, let's see, my right-hand side has an a right now from here, and I'll put a minus o here. Right, so my right-hand side of this, in terms of the three coordinates, are going to be the x-coordinate of a minus the x-coordinate of the ray origin, the x-coordinate of the y-coordinate minus the origin y, and I keep substituting the wrong variable. I want to keep a the same and substitute the subscript z minus oz. And let's see if I can write my matrix. I better write small. What multiplies beta is b minus a. So for the x component, let's see, the x component of this equation is going to say bx minus ax times beta, and then it's going to be cx minus ax times gamma, and then it's going to be, I think I made a mistake here. This should be minus, shouldn't it? Because I was writing what was on this side of the equation. Maybe let's see, did I? Yeah, these should be backwards, right? If I'm bringing these to the same side as the this and putting my O on the other side, this should be A minus C. It should change signs, right? Is that correct? Because I brought these terms to the left-hand side of the equation. A minus C and B minus C. So yeah, that's what I'm not sure what I have. I have AX minus BX here, so I guess, yeah, my notes agree. AX minus BX, and then gamma is, no, it's not B minus C. It's, if I change the sign of this, it's A minus C. Okay, is my algebra right now? Did I, yeah, A minus B here. Thank you. Now it's right. Sorry. I tend to make lots of algebra mistakes in my lectures. Even if my notes are okay, which I think they are in this case, I sort of go on autopilot trying to copy things from the board, and I make lots of mistakes. So please correct me. Let's see. So now the x component, now this is going to be AX minus CX, and the x component of this is going to be DX. And similarly, AY minus CY. Nope. Substitute the wrong thing again, didn't I? AY minus BY, AY minus CY, and DY. And this is going to be AZ minus BZ, AZ minus CZ, and DZ. Okay, so I've given the matrix form of the three equations and three unknowns. Right? This times this plus this times this plus that times that equals this, which is the x component of this equation. So we get three equations and three unknowns, and what the book suggests that I Xeroxed for you is just use Cramer's rule, which is an explicit formula, and the complete explicit formula is written in there. You could just copy it. He makes even a point there's some common sub-expressions that either you could set out explicitly or hope if you write it correctly, even the compiler will find the common sub-expressions, because you've got Cramer's rule has a determinant for the denominator and three determinants for the numerator. And so you're going to find beta, gamma, and t. And then you're going to check these inequalities for beta and gamma. And if it satisfies those three inequalities, then the ray intersection is inside the triangle. And if the t is positive, then you know it's in the direction you're looking along the ray instead of behind your eye. And if the ray is parallel to the plane, then you've got a problem, because the denominator will be 0. Your denominator turns out to be basically this normal vector dot the direction vector. And if that's 0, that means that you're dividing by 0. So that's not going to work. If your ray is parallel to the plane but not inside the plane, then it doesn't intersect the plane. If your origin of the ray is on the plane, then I guess you have to use a different computation to figure out, because you're really going to run into an edge of the triangle first inside that plane. So you have to have a special case for that. So now I want to discuss a way of that's going to end up resulting with 4 determinants, another way of looking at this, which works for quadrilaterals and other convex polygons. So maybe I'll go back to, let's see, can I go back to this picture here? We've computed the normal vector, and we find this point. We want to know whether this point is inside the triangle. One way to do it is to make a kind of a pyramid. Let me keep this point in the plane, but let me make it the origin. Where can I make the origin so the pyramid is clearer? I guess if we were looking at this plane, this would be dotted, right? Because this is the front face, and here are 2 back faces of the pyramid. And we want to know, is this point P that we get just by solving this one linear equation in a single unknown to get a 3D point somewhere on the plane, which is easier than solving those 3D equations and also finding beta and gamma. Is that point inside this pyramid? So what we can do is we can, just like I found a normal to this plane by taking this cross product here, I can find the normal to this plane by, say, taking the origin minus A. I have to figure out, let me write it and then I'll try and figure out whether I've done it consistently. The origin minus B. Okay, so the A was this vertex up here. And if I take this with my right hand rule, I'm going to get a normal that's pointing, in this particular case, inside this triangle. And then I just have to evaluate P with respect to that plane equation to see if it's on the positive side of the plane. Right? So I take P minus A dot this cross product. O minus A cross O minus B. And if that is positive, then in this particular case, P is inside the pyramid. At least it's on the correct side of this pyramid face. And then I similarly take, where will I write it? I can get a similar equation for this face here. O minus B cross O minus C. Let's see. Right? If I do like that, I'm pointing toward the inside of this pyramid. And so if I take that, it doesn't matter which order I take the dot product, so I'll write it this way. Times O minus P. So if this is greater than 0, or say greater than or equal to 0, and this one is greater than or equal to 0, and O minus, let's see, I'm going to take O minus C cross O minus A, which is sort of behind here, and I'm going to get a vector that's pointing up from this bottom face. And if P is positive too, that's if dot product is positive, it's on the inside, because these are inward pointing normals. O minus B, let's see, what did I say? O minus C, sort of permuting the order, going back to the first one. So it's each vertex and the next vertex, and then you go back to the first vertex again. Let's see, do I want O minus P or P minus O? I did this backwards, didn't I? I said O minus P, but really it's P minus O. The way I did this is the point on the plane, and this is the point that I'm testing. So each of these was written backwards. I did P minus A, okay, here. This should have been, no, it's P minus O here. I wrote that wrong. This is P minus O. No, it's P minus, let me think about this. It's, the O is always on the plane, because I'm always taking one of these planes through the origin. So it's always P minus O here and P minus O here. If all these three things are greater than 0, it's inside. But that's only on the, because normally if you have a face, you're getting an outward normal. Like if we take B minus A cross C minus A, we get the outward normal here, because this was counterclockwise when viewed from outside. And here, this one we did, how did I write this? This one is clockwise when viewed from outside. C, B is clockwise. So basically, there's a sign test here. If the viewpoint makes this triangle look clockwise, then these tests should be greater than or equal to 0. But if the viewpoint makes the triangle look counterclockwise, then the test should be less than or equal to 0. So one way to think about that is to say, if we take each of these products and either multiply or divide by the, how can I say it now? If we take O minus A dot this normal, or any point on the triangle here, dot the normal, that'll tell us, in this case, it will be negative, right? Because this thing is pointing away from us. So what we can say is, if this is negative, then you use a plus sign. I mean, you insist these be greater than or equal to. Whereas if this thing is positive, you insist it being less than or equal to. Now, it turns out that this, if you take the cross product of two vectors, and then take a dot product with a third, it's the same as a determinant. Right? Because basically, you can think of the way you compute the volume of this. It's a sixth of the volume of a parallelepiped, and the volume of a parallelepiped is that determinant. So these are all proportional to determinants. So you still have to take 4 determinants in order to find these tests. 1, 2, 3, and then this fourth to determine which sign you're going to use, depending on the orientation. So you've done the same amount of arithmetic by this method as the other. And if you did a little algebra, you might even find their equivalent. But I doubt it, because this, yeah, no, it could be, because, you know, these things have O's in them here. Could end up being exactly the same arithmetic. I'm not sure. But the advantage is that that one works for any convex polygon, right? If you have A, B, C, D, let's see, where will I write it? Maybe on this board. Well, let me draw a pentagon. A, B, C, D, E. And this pentagon is in some slanted plane here, and we have the origin here and a direction vector here. We can do the same thing, right? We can intersect that ray with the plane. We can get the plane equation by any 3 points as long as they're not collinear. We can find out the point where the ray intersects the plane, and then we could check if that point was inside all the faces of this pentagonal pyramid. Right? We could just use the single. I mean, if you look at just ABC, you could test, whether that is clockwise or counterclockwise with respect to O, and that would give you the sign to make sure you were consistently getting the signs of the other tests correctly. And then you could do 5 other tests, which amount to 5 other determinants, and you could decide if this point was inside. So I guess in that case you'd be saving work, because the other alternative would be to divide this pentagon into 3 triangles and do the other method with the linear equations for all 3. And then that would be 3 times 4 is 12 determinants, where this is only 5 plus 1 is 6 determinants. But that method doesn't work for a non-convex polygon, right? Because then it's going to be hard for me to draw the pyramid, but let me just draw on this board a non-convex polygon, and we'll just think of, are you in the, and basically we have the inside of this plane, the inside of that plane, the inside of that plane, the inside of that plane, and the inside of that plane. And so the question is, if you're on the inside of all these planes, is that necessary and sufficient to be inside here? And I think it's probably sufficient, but I'm not sure it's necessary, because actually the only thing that satisfies all these inequalities is this region here, right? And you're missing a whole lot of the triangle because of this, I guess, sort of concave pentagon, because we've got pieces here which are on the wrong side of this line, but nevertheless on the inside this pentagon. So this method in general only works for convex polygons. And if you have a concave polygon, I think you really have to divide it into 3 triangles. But if you're building models out of quadrilaterals, you might have convex quadrilaterals too, I guess. But in general, like if you were drawing a sphere in terms of polygons that were like triangles around the North Pole and then latitudes and longitudes, those are sort of parallel, they're not convex. So if you can guarantee your polygons are not convex, you can use this method to intersect an arbitrary polygon. Okay, so let's see. Is there anything else I want to say? I think I'm finishing early again. Does anybody have any questions? Well, I guess we can't get remote questions. Let me think if there's anything useful I can say in terms of the homework. Yes, there is. When I asked you to do the recursive ray tracing with diffuse and perfect mirror, so that you don't have to do like the Phong specular highlight, because we're going to assume that any mirror reflection is perfectly shiny. We're just going to allow the surface to be a sort of a linear combination of somewhat a diffuse color and a specular color. And the specular coefficient that you're going to use, it could be colored too. Like you could think of reflecting in a red Christmas tree ball, and sort of reflects more of the red color that's bouncing on it than the green and the blue color. And then I think I use the analogy with this Christmas ball is sort of dusty. It's been, sitting on the tree all year. And it's accumulated a dot of dust, and the dust reflects diffusely. So the part when your viewing ray hits the dust, you're probably seeing a diffuse reflection, maybe gray diffuse. And then when your eye doesn't hit a dust particle, maybe you're seeing a specular reflection. It's got a red tint to it. So there is a sort of a physical plausibility for a surface that partly perfect mirror and partly diffuse. But you know, often you want to just make it either diffuse with their specular coefficient non-zero, and the zero, and the diffuse non-zero, or vice versa. I was just allowing for both. And I'll repeat what I said last time. When I wrote that code, I sort of didn't write the possibility that you also trace a refracted ray, because I didn't want you to bother with refraction on this homework. So it's just, you know, either code one of these ray triangle things and build your model out of triangles, or I guess the default model, I just had one sphere and one light source, and I only want a point light source now, and I just want to see the multiple reflections and the fact that you've actually got ray tracing going, and then on future assignments you can add these other effects we're going to be talking about next. Okay, I was pretty sure this lecture was going to end early because I didn't have that much to say, but I'll see you on Wednesday.